Welcome to Slumbertainment. Get comfortable, close your eyes, and let yourself relax. Tonight we explore the history of roads. Please like and subscribe for more restful content. Now, let's begin. Long before humans walked upright, paths were being carved into the earth. Animals moving between water sources and grazing grounds created the first corridors through wilderness, their hooves and paws compacting soil in predictable patterns. These trails followed the contours of least resistance, avoiding steep grades and seeking firm ground. When early humans began to migrate and hunt, they inherited these routes, recognizing that generations of animal movement had already solved the fundamental problem of navigation through complex terrain. The first deliberate roads emerged when human settlements became permanent. Around 8,000 years ago in Mesopotamia, in what is now modern-day Iraq, communities began to recognize that the spaces between dwellings and fields required maintenance. Rain turned pathways into ribbons of mud. Repeated foot traffic in wet conditions created ruts that deepened with each passing season. The solution was elegant in its simplicity. Flat stones pressed into the mud created stable surfaces that shed water rather than absorbing it. These weren't roads in any formal sense, but they represented humanity's first intentional intervention in the challenge of movement across Earth. The development of wheeled vehicles around 3500 BCE transformed the requirements for roads entirely. A path sufficient for human feet or animal hooves became inadequate when subjected to the concentrated weight and repetitive stress of wooden wheels. The Sumerians, who inhabited southern Mesopotamia, began to understand that roads required engineering rather than merely designation. They observed that certain types of clay soil, when properly prepared and compacted, could support wheeled traffic without deteriorating. The process involved removing the loose topsoil, filling the excavation with gravel or crushed stone, and then covering this foundation with smaller stones that locked together under pressure. This layered approach to road construction represented a profound insight into materials behavior. The bottom layer of large stones distributed weight across a broader area, preventing the road from sinking into the underlying soil. The upper layer of smaller stones created a relatively smooth surface, while allowing water to drain through gaps between the stones rather than pooling on the surface. This principle of stratified construction, with each layer serving a specific structural purpose, would remain fundamental to road building for millennia. The ancient Egyptians faced a different challenge. The Nile River provided the primary transportation corridor, but moving the massive stone blocks required for pyramid construction demanded overland routes capable of supporting extraordinary loads. Around 2600 BCE, during the construction of the pyramids at Giza, Egyptian engineers developed specialized roads for hauling stones from quarries. These weren't permanent structures in the traditional sense, but rather temporary pathways designed for specific projects. Workers would cut trenches in the bedrock, creating tracks with raised edges that guided wooden sledges loaded with multi-ton stone blocks. The trenches were then filled with a slurry of wet Nile mud, which served as a lubricant, dramatically reducing the friction between sledge and road. Archaeological evidence suggests that these Egyptian hauling roads incorporated an understanding of moisture management that was remarkably sophisticated. By maintaining the mud at optimal wetness, workers could reduce the force required to move heavy loads by as much as half. Too dry, and the sledge would bind against the surface. Too wet, and the sledge would sink into the mire. This attention to the relationship between materials, moisture, and friction represented early applied physics, even if the Egyptians didn't frame it in those terms. The Minoans on the island of Crete, around 2000 BCE, developed what may be the first paved roads designed primarily for wheeled traffic rather than ceremonial purposes. These roads connected the palace at Knossos with other settlements across the island. Minoan engineers cut flagstones to relatively uniform dimensions and fitted them together with remarkable precision. They understood that water was the enemy of road longevity and incorporated crown surfaces that shed rainwater to drainage channels running alongside the road. The crown, a gentle convex curve across the road's width, ensured that water flowed to the edges rather than pooling in the centre where wheels would pass most frequently. What distinguished Minoan roads was their integration with the broader landscape. Engineers didn't simply lay stones on existing ground, but rather excavated foundations, sometimes cutting through rock to maintain consistent grades. They recognised that a road climbing a steep slope would be prone to erosion and structural failure, so they developed techniques for creating switchbacks and terracing hillsides. This represented a shift in thinking from roads as surfaces to roads as engineered systems that had to account for geology, hydrology, and topography. By 1500 BCE, the Hittites in Anatolia, in modern-day Turkey, were constructing roads that served military and commercial purposes across challenging mountainous terrain. Hittite roads incorporated many Minoan innovations, but added new elements suited to their geography. In regions where stone was scarce, they developed techniques for stabilizing earth roads, using lime mixed with clay, creating a primitive form of cement that hardened when exposed to air and moisture. This binding agent allowed them to construct durable roads, even where suitable paving stones weren't available. The technological exchange between civilizations accelerated road development. Traders and armies travelling between Mesopotamia, Egypt, Anatolia, and the Mediterranean islands carried knowledge of construction techniques along with their goods and weapons. A Phoenician merchant observing Egyptian road construction might incorporate those principles into projects in his home city. A captured engineer might find himself building roads for his conquerors using methods from his homeland. This cross-pollination of ideas meant that by the end of the Bronze Age, around 1200 BCE, a body of practical knowledge about road construction had accumulated across the ancient Near East and Eastern Mediterranean. These early roads were more than transportation infrastructure. They represented humanity's growing confidence in reshaping the natural world to serve collective purposes. A road required coordinated labour, planning that extended beyond immediate needs, and resources dedicated to a structure that might take years to complete. The decision to build a road reflected a society's assessment that the future benefits of improved transportation justified present costs. Roads made trade more efficient, military campaigns more feasible, and communication between settlements more reliable. In this sense, the history of roads is inseparable from the history of civilization itself. Each advance in road technology enabling corresponding advances in social complexity and economic integration. The Romans transformed road construction from a practical craft into a systematic science. Beginning around 300 BCE, Roman engineers developed construction methods so effective that many of their roads remain visible and even functional more than 2,000 years later. What distinguished Roman roads wasn't any single innovation, but rather the integration of multiple techniques into a standardized system that could be replicated across diverse terrain and climates. Roman road construction began with surveying. Engineers called agrimensores used specialized instruments to establish straight lines across landscapes, often ignoring natural contours in favor of directness. The groma, a wooden cross with plumb lines hanging from each arm, allowed surveyors to establish right angles and maintain consistent alignment over long distances. This commitment to straightness served military purposes, enabling legions to move quickly between strategic locations, but it also created engineering challenges that demanded sophisticated solutions. Once the route was established, construction crews excavated a trench typically between 3 and 5 feet deep, depending on soil conditions. The width varied by road classification. Major arterial roads, the Viae Publicae that connected Rome to distant provinces, might span 15 to 20 feet in width. Secondary roads were narrower, sometimes as little as 8 feet across. The depth of excavation reflected Roman understanding that a road's foundation had to extend below the frost line in colder climates, preventing the heaving and cracking that occurred when frozen ground expanded and thawed. The foundation layer, called the statumen, consisted of large flat stones set directly on the exposed soil at the bottom of the trench. These stones were positioned carefully to create a stable base, with gaps between them filled with smaller stones and mortar made from lime and volcanic ash. Roman engineers had discovered that volcanic ash from deposits near Mount Vesuvius, when mixed with lime and water, created a hydraulic cement that hardened even underwater. This pozzolana cement, named after the town of Pozzuoli, where significant ash deposits existed, gave Roman construction exceptional durability. Above the statumen came the rudus, a layer of broken stones mixed with lime mortar or sand. This layer, typically 9 to 12 inches thick, served multiple purposes. It distributed the weight of traffic across the foundation stones, filled irregularities in the lower layer, and provided additional drainage capacity. The stones in the rudus were crushed to relatively uniform sizes, usually 2 to 4 inches in diameter, allowing them to pack tightly while still permitting water to percolate downward rather than accumulating in the road structure. The third layer, the nucleus, consisted of finely crushed stone, gravel, or sand mixed with lime cement. This layer, usually 6 to 9 inches thick, created a smooth bed for the road surface while providing a final filtration layer for water drainage. The nucleus had to be compacted thoroughly, and Roman construction crews developed techniques using weighted rollers and repeated ramming with heavy timbers to achieve maximum density. Proper compaction was critical because any settling after the road was completed would create depressions where water could accumulate. The uppermost layer, the summum dorsum, was the visible road surface. On major roads, this consisted of large flat paving stones called silex, typically basalt or other hard volcanic rock, cut to polygonal shapes that fitted together tightly. These stones, often 8 to 12 inches thick, were positioned with slight gaps between them, which were filled with sand or fine gravel. The surface was crowned, rising several inches from the edges to the centre, ensuring that rainwater flowed to drainage ditches excavated alongside the road. The crown typically rose at a rate of about 1 inch per foot of width, creating a noticeable but not uncomfortable slope. The total depth of a major Roman road, from paving stones to foundation, often exceeded 3 feet. This massive investment of materials and labour reflected Rome's strategic priorities. Roads enabled rapid deployment of military forces, facilitated tax collection by allowing officials to reach distant provinces, and promoted economic integration by reducing the cost of moving goods. The Via Appia, begun in 312 BCE by the censor Appius Claudius Caecus, eventually stretched over 350 miles from Rome to Brindisi on the Adriatic coast. Its construction required moving thousands of tons of stone and employed crews numbering in the thousands. Roman roads incorporated sophisticated drainage systems beyond the crowned surface. Culverts carried streams and runoff under the road, preventing water from undermining the foundation. These culverts were often constructed from shaped stone blocks forming an arch, demonstrating Roman mastery of arch engineering. The arch distributed the weight of the road and traffic above it across a broader area, allowing relatively thin stone structures to support enormous loads. In marshy areas, Roman engineers drove wooden piles into the soft ground to create artificial foundations, then built the road structure atop these pilings. The edges of Roman roads often featured raised curbs made from large squared stones. These curbs served multiple purposes. They contained the road structure, preventing the edge stones from shifting outward under traffic loads. They defined the road clearly, important for legal purposes, since Roman law recognized roads as public property with specific rights and restrictions. They also provided a mounting aid for riders and marked the boundary of the drainage ditches that ran parallel to most roads. Roman roads varied in quality based on their strategic importance and the availability of materials. In regions where suitable stone was scarce, such as parts of North Africa, engineers adapted by using local materials. Desert roads might have surfaces of compacted sand mixed with gravel, reinforced with lime mortar where available. In provinces like Britannia, modern-day Britain and Wales, where the climate was wetter, Roman engineers paid particular attention to drainage, sometimes elevating roads on embankments called ageres to lift them above the surrounding water table. The Romans also developed specialized roads for specific purposes. The Via Glarii were gravel roads, less durable than paved routes, but sufficient for local traffic and much faster to construct. In mountainous regions, engineers cut roads into cliff faces, sometimes creating galleries where the road ran beneath a rock overhang. The Via Claudia Augusta, crossing the Alps between the Roman provinces of Italia and Germania, included sections where the road was carved directly from living rock, with notches cut to provide footing for pack animals. Maintenance systems ensured that Roman roads remained functional across centuries. Local communities bore responsibility for maintaining roads passing through their territory, overseen by imperial officials called curatores viarum. Milestones placed at regular intervals recorded distances and identified which emperor or official had constructed or repaired that section of road. These stones, many still standing today, provide historians with detailed records of Roman road networks and construction chronology. By the 2nd century CE, Rome had constructed approximately 50,000 miles of paved roads throughout the empire, with perhaps an additional 200,000 miles of secondary roads. This network connected Britain to Mesopotamia, modern-day Iraq, and North Africa to the Danube. The standardization of construction methods meant that a road in Hispania, modern-day Spain, was built to similar specifications as one in Syria, creating a transportation infrastructure of unprecedented scale and consistency. The collapse of the Western Roman Empire in 476 CE marked the beginning of a long decline in road infrastructure across Europe. The maintenance systems that had preserved Roman roads for centuries disappeared as centralized authority fragmented into smaller kingdoms and feudal territories. Without coordinated oversight or the resources to fund repairs, the great paved highways began to deteriorate. Frost penetrated cracks in the paving stones, expanding and contracting with seasonal cycles, gradually breaking apart surfaces that had remained intact for centuries. Vegetation took root in gaps between stones, with roots prying apart the careful stonework. Drainage ditches filled with sediment, causing water to pool on road surfaces rather than flowing away, accelerating the breakdown of foundations. Medieval Europe saw road construction and maintenance become localized and irregular. The responsibility for roads often fell to monasteries, which maintained routes between religious houses, or to feudal lords, who kept roads passable within their domains, primarily for military purposes. The concept of roads as public infrastructure, serving broader economic and social purposes, largely disappeared. Instead, roads became pragmatic responses to immediate needs, rather than components of an integrated transportation system. The quality of medieval roads varied dramatically by region and purpose. Major pilgrimage routes, such as those leading to Santiago de Compostela in modern-day Spain or Canterbury in England, received better maintenance because of the economic benefits religious tourism brought to communities along the way. Merchant routes connecting important trading centres sometimes benefited from collective maintenance agreements between cities. Most roads, however, were simply cleared paths through forests or across fields, unmarked and unmaintained, often impassable during wet seasons when mud made travel impossible for wheeled vehicles. Where Roman roads still existed, they continued to be used, though often in degraded condition. The paving stones, valuable as building material, were sometimes quarried by local populations for construction projects. Sections of Roman roads disappeared entirely as farmers ploughed over them or builders dismantled them for stone. Other sections remained in use precisely because they were so well constructed that even without maintenance they remained superior to any alternative. The Via Appia continued to carry traffic throughout the medieval period, though its condition deteriorated significantly from its Roman-era state. Medieval road construction, when it occurred, typically reverted to simpler methods. Workers would clear a path, remove obstacles, and perhaps add gravel or crushed stone to provide a firmer surface. The multi-layered Roman approach, with its foundation stones, binding cement, and carefully fitted paving, was beyond the technical capabilities or economic resources of most medieval communities. The knowledge of hydraulic cement was lost in Western Europe and wouldn't be rediscovered until the 18th century. Roads were built to be functional rather than durable, with the expectation that they would require frequent repairs. Bridge construction similarly declined. Roman stone bridges had spanned rivers throughout the empire, but maintaining these structures required specialized engineering knowledge and significant resources. Medieval bridges were often wooden structures, rebuilt frequently after floods or decay. Stone bridges, when constructed, tended to be narrow and steep, designed primarily for foot traffic and pack animals rather than wagons. The famous medieval bridge at Avignon in modern-day France, begun in 1177, took decades to complete and became renowned precisely because substantial stone bridges had become so rare. While European road infrastructure declined, other regions maintained more robust transportation networks. In China, the Tang dynasty, spanning from 618 to 907 CE, maintained an extensive road system connecting the capital at Chang'an in modern-day Shaanxi province with distant provinces. These roads served both administrative and military purposes, with relay stations positioned at regular intervals where official messengers could change horses. Chinese roads of this period typically featured rammed earth foundations, compacted through repeated pounding with heavy wooden mallets. In some regions, particularly in the south where rainfall was heavy, roads were paved with stone slabs similar to Roman techniques, though the construction methods had developed independently. The Inca Empire in South America, which flourished from the 13th to 16th centuries, developed one of the most impressive road systems of the pre-modern world despite having no wheeled vehicles. The Capac Nan, or Royal Road, stretched for approximately 25,000 miles across diverse terrain ranging from coastal deserts to high mountain passes in the Andes. Inca roads were engineered with remarkable sophistication, incorporating switchbacks on steep slopes, stone staircases where grades were too steep for gradual ascent, drainage channels to prevent erosion, and suspension bridges made from woven grass cables spanning river gorges. Inca road construction adapted to local geography and materials. In mountainous regions, roads were often carved directly into cliff faces or built up with retaining walls of fitted stone. In marshy areas, causeways elevated the road surface above water. In deserts, roads were sometimes marked by rows of wooden posts rather than constructed surfaces, providing navigation aids in featureless terrain. The roads served as arteries for the empire's communication system, with runners called chasqui carrying messages between relay stations, and for moving armies and administrators throughout the realm. In the Islamic world, the expansion of trade networks across North Africa, the Middle East, and into Central Asia necessitated maintained roads, particularly along major caravan routes. Islamic engineers preserved and expanded upon Roman road-building techniques in regions that had been part of the Roman Empire, such as North Africa and the Levant. The introduction of caravanserais, fortified roadside inns positioned at regular intervals along trade routes, created infrastructure that supported long-distance commerce. These structures provided security for merchants and their goods, access to water, and facilities for maintaining pack animals. The Silk Road, though often conceived as a single route, was actually a network of interconnected roads and paths linking China with the Mediterranean world. The eastern sections passed through Chinese territory, following well-maintained imperial roads. The central portions crossed territories controlled by various kingdoms and empires, where road quality depended on local political stability and economic priorities. The western sections connected to Byzantine and later Islamic road systems. Throughout its length, the Silk Road's success depended not on any single authority maintaining the route, but on the collective interest of merchants, local rulers, and communities who benefited from trade. European road conditions began to improve gradually in the late medieval period as economic activity intensified and centralised monarchies emerged with greater capacity to fund infrastructure. In England, the Statute of Winchester in 1285 required landowners to maintain roads passing through their property and to clear vegetation for 200 feet on either side of highways to reduce opportunities for banditry. This represented an early attempt to establish legal responsibility for road maintenance, though enforcement remained inconsistent. By the 14th century, some European cities began to pave streets within their walls. These urban paving projects typically used cobblestones, rounded stones gathered from riverbeds or fields, and fitted together to create a relatively durable surface. Cobblestones were smaller and easier to work with than the large cut stones Romans had used, and they could be replaced individually when damaged. The rounded surface shed water reasonably well, though the gaps between stones created an uneven surface that made wheeled traffic uncomfortable and noisy. Nevertheless, cobbled streets represented a significant improvement over mud and marked the beginning of renewed attention to urban transportation infrastructure. The transition from medieval neglect to renewed investment in roads would accelerate in the following centuries, driven by expanding commerce, growing state capacity, and gradual recovery of classical engineering knowledge. The roads that had once connected a unified empire would eventually be rebuilt to serve nations and emerging markets, though the path to that revival would prove long and uneven. The Renaissance brought renewed interest in classical knowledge, including Roman engineering treatises that had been preserved in monasteries throughout the medieval period. By the 15th century, European scholars were translating and studying works like Vitruvius's De Architectura, written in the 1st century BCE, which contained detailed descriptions of Roman construction techniques. This rediscovery of ancient knowledge coincided with political and economic changes that made road infrastructure increasingly important to emerging nation-states. France under King Louis XIV, who reigned from 1643 to 1715, established the Corps des Ponts et Chaussées, a body of civil engineers responsible for roads and bridges throughout the kingdom. Created in 1616 and formalised as a professional organisation by 1681, this corps represented the first systematic approach to road infrastructure since the Roman Empire. Engineers trained at the École des Ponts et Chaussées, founded in 1747, studied mathematics, mechanics, and material science, applying these principles to road design. French roads of this period began to incorporate engineering calculations for grades, curves, and foundation depths, rather than relying solely on traditional practices. The techniques developed by French engineers spread throughout Europe. Pierre-Marie Jérôme Tresaguet, who served as Inspector General of Roads in the Limoges district from 1764 until his death in 1796, developed a construction method that influenced road building for generations. Tresaguet's approach involved excavating a trench and laying large foundation stones with their flat sides vertical rather than horizontal, creating a wall-like structure that distributed weight laterally. Above this foundation came a layer of smaller broken stones, topped with a carefully graded surface of fine gravel. The total depth was significantly less than Roman roads, typically around 10 inches, making construction more economical while still providing adequate support for the wheeled traffic of the period. Britain developed road infrastructure through a different mechanism: turnpike trusts. Beginning in the late 17th century, Parliament granted groups of investors the right to improve specific roads and collect tolls from users to fund construction and maintenance. The first Turnpike Act was passed in 1663 for a section of the Great North Road in Hertfordshire, Huntingdonshire, and Cambridgeshire. By the mid-18th century, hundreds of turnpike trusts operated throughout England and Wales, creating a network of improved roads connecting major cities and commercial centres. Turnpike roads varied considerably in quality depending on the resources and expertise available to each trust. Some trusts employed skilled engineers who implemented advanced construction techniques, while others simply added gravel to existing dirt roads. The toll system created economic incentives for improvement, since better roads attracted more traffic, generating higher revenues. However, tolls were often unpopular with local populations who had previously travelled on poor but free roads and now faced fees for passage. John Metcalfe, known as Blind Jack of Knaresborough, constructed numerous turnpike roads in Yorkshire and Lancashire between 1765 and 1792, despite having lost his sight to smallpox as a child. Metcalfe developed techniques for building roads across moorland and bog by laying bundles of heather as a foundation, creating a flexible but supportive base that distributed weight across soft ground. His work demonstrated that engineering principles could be adapted to challenging terrain through creative application of local materials. Thomas Talfourd, born in 1757 in Scotland, became one of the most influential road engineers of the late 18th and early 19th centuries. Appointed Surveyor of Public Works for Shropshire in 1787, Talfourd eventually designed over 900 miles of roads throughout Britain. His method involved excavating to firm subsoil, laying foundation stones by hand to create a solid base, covering this with a layer of broken stone 7 inches deep, and topping the surface with an inch of gravel. Talfourd specified that stones should be broken to specific sizes, that the surface should be crowned for drainage, and that construction should be supervised carefully to ensure proper technique. Talfourd's roads featured gentler grades than previous construction, often requiring substantial earthworks to achieve acceptable slopes. He calculated that horses could pull heavier loads on well-graded roads, making the additional construction cost economically justified. His London to Holyhead Road, completed in 1826 to improve communication with Ireland, included sections cut through rock and elevated on embankments, demonstrating engineering ambition comparable to Roman projects. The road maintained grades of no more than 1 in 30 where possible, a significant improvement over medieval roads that often climbed hills at whatever angle the terrain dictated. John Loudon McAdam, born in 1756 in Scotland, developed a road construction system that proved even more influential than Telford's approach. McAdam observed that roads failed primarily because water penetrated the road structure, weakening foundations and creating ruts. His method, developed while serving as surveyor to the Bristol Turnpike Trust beginning in 1816, emphasised drainage and compaction over heavy foundation stones. McAdam's roads were built directly on the native soil, provided it was properly drained and crowned. He specified that broken stones, each small enough to fit in a worker's mouth, approximately 1 inch in diameter, should be spread in thin layers and compacted by traffic rather than laid in thick beds. The McAdam method relied on the stones interlocking under the pressure of wheels and hooves, with fine stone dust filling the gaps to create a relatively waterproof surface. This macadamization process required less material and labour than traditional methods, making road construction significantly more affordable. The technique spread rapidly throughout Britain and internationally. By the 1830s, macadamized roads were being constructed across Europe and in the United States, where expanding settlement demanded economical road-building methods. Macadam's system worked best in climates where roads didn't experience severe frost heaving. In colder regions, engineers adapted the technique by adding foundation layers similar to those Telford specified, creating a hybrid approach. The key insight from McAdam's work was that careful attention to surface drainage and proper stone sizing could create durable roads without massive foundation investment, democratizing road construction by making it accessible to communities with limited resources. The development of steam-powered vehicles in the early 19th century created new demands on road infrastructure. Steam carriages weighing several tons damaged macadamized surfaces designed for horse-drawn traffic. The metal wheels of steam vehicles crushed the interlocked stones, creating ruts and requiring frequent repairs. This led to experiments with alternative surface materials, though truly effective solutions wouldn't emerge until the widespread adoption of petroleum-based binders later in the century. By the mid-19th century, Europe and increasingly North America had developed road networks that, while not approaching Roman standards of durability, were vastly superior to medieval conditions. The combination of engineering knowledge, economic incentives from toll systems, and competition between regions to attract commerce had transformed road construction from a lost art into a systematic practice. Engineers understood the importance of foundations, drainage, compaction, and surface materials, applying these principles consistently across thousands of miles of roadway. The stage was set for further innovation as Industrial Revolution technologies began to influence transportation infrastructure. The discovery that petroleum-derived materials could bind road surfaces together marked a transformative moment in road construction history. Natural asphalt had been known since ancient times, occurring in deposits where crude oil seeped to the surface and volatile components evaporated, leaving behind a sticky black residue. The ancient Mesopotamians had used natural asphalt as waterproofing and mortar, but its application to road surfaces wouldn't be systematically explored until the 19th century. In 1832, French chemist Edmond Peclet conducted experiments mixing natural asphalt from deposits at Val de Travers in Switzerland with sand and crushed limestone, creating a material that could be heated and spread to form a smooth, water-resistant surface. The first asphalt pavement was laid on the Pont Royal in Paris in 1854, demonstrating that this material could withstand traffic and weather better than traditional stone surfaces. The asphalt surface remained flexible rather than rigid, allowing it to accommodate slight movements in the underlying foundation without cracking. Belgium pioneered the use of natural rock asphalt for road construction on a larger scale. In 1870, a major street in Brussels was paved with compressed rock asphalt from deposits in France. The material was crushed, heated to approximately 200 degrees Fahrenheit, and spread while still hot, then compacted with heavy rollers. As it cooled, the asphalt solidified into a hard but slightly elastic surface that was smooth, relatively quiet under traffic, and easy to keep clean. These qualities made asphalt particularly attractive for urban streets where dust from stone roads had become a persistent problem. The United States began experimenting with asphalt paving in the 1870s. Pennsylvania Avenue in Washington, D.C. received an experimental asphalt surface in 1876 using natural asphalt imported from Trinidad. The project succeeded well enough that other cities began to adopt the material. By 1890, there were approximately 400 miles of asphalt-paved streets in American cities, concentrated primarily in the Northeast and Midwest. The invention of the automobile at the end of the 19th century created unprecedented demands on road infrastructure. Early automobiles, with their rubber tires and relatively high speeds, generated different forces than horse-drawn vehicles. The pneumatic tire, invented by John Boyd Dunlop in 1888, created suction effects on road surfaces as the tire lifted off the pavement, pulling up dust and loose stones. Macadamized roads, which had performed adequately for horse traffic, disintegrated rapidly under automobile use, creating clouds of dust that made driving unpleasant and unhealthy. The solution emerged from combining macadam's stone construction principles with bituminous binders. Edgar Purnell Hooley, a British surveyor, noticed in 1901 that a barrel of tar had accidentally spilled on a macadamized road and been covered with slag waste from a nearby ironworks. The area remained smooth and free of dust, despite heavy traffic. Hooley patented a process he called tarmac, which involved mixing coal tar with stone aggregate and spreading it as a surface layer. The tar bound the stones together while filling voids, creating a surface that resisted both water penetration and the suction effects of pneumatic tyres. Tar macadam construction involved heating coal tar, a byproduct of coal gas production, to reduce its viscosity. Workers mixed the heated tar with stone aggregate in specific proportions, typically 1 part tar to 12 parts stone by weight. This mixture was spread on a prepared base, usually existing macadam that had been cleaned and graded, then compacted with heavy steam rollers weighing 10 tons or more. The rollers, introduced in the 1860s but essential to tar macadam construction, compressed the material while it was still warm, forcing the tar to fill voids between stones and creating a dense, cohesive surface. The rise of petroleum refining in the late 19th century provided an alternative to coal tar. Asphalt, a residue from petroleum distillation, could be used similarly to coal tar but had different properties. Asphalt remained more flexible across temperature ranges, making it better suited to climates with extreme seasonal variation. Petroleum asphalt also lacked some of the toxic compounds present in coal tar, though this wasn't a primary concern at the time. By the early 1900s, both tar macadam and asphalt macadam were being used extensively, with material choice often depending on local availability and cost. The Good Roads movement in the United States, beginning in the 1880s, advocated for improved rural roads to benefit farmers and enable automobile tourism. This campaign led to increased government involvement in road construction, with states beginning to establish highway departments and provide funding for road improvement. New Jersey created the first state highway department in 1913. The Federal Aid Road Act of 1916 provided matching funds to states for road construction, marking the federal government's entry into road infrastructure funding. World War I demonstrated the strategic importance of road infrastructure for military logistics. The movement of troops, equipment and supplies by motor vehicle required extensive road networks capable of supporting heavy loads. European nations, particularly Germany and France, invested heavily in road construction during and after the war. The German Reichsautobahn project, begun in the 1920s, aimed to create high-speed motorways connecting major cities, though economic difficulties delayed extensive construction until the 1930s. The mechanization of road construction accelerated dramatically in the early 20th century. Steam shovels excavated roadbeds faster than hand labour. Mechanical crushers processed stone aggregate to precise specifications. Asphalt mixing plants could produce hundreds of tons of material per day, far exceeding what was possible with manual methods. Motor trucks transported materials to construction sites efficiently. Improved rollers, both steam-powered and later diesel, compacted surfaces more thoroughly than was achievable with horse-drawn equipment. The development of Portland cement concrete provided another paving option. Joseph Aspdin patented Portland cement in England in 1824, but its use in road construction came later. Concrete roads offered exceptional durability and load-bearing capacity. The first concrete street in the United States was built in Bellefontaine, Ohio, in 1891. Concrete construction involved creating forms to contain the wet mixture, pouring concrete to a specified depth, typically 6 to 8 inches for roads, and finishing the surface before the concrete hardened. Steel reinforcement, introduced in the early 1900s, reduced cracking by absorbing tensile stresses that concrete alone couldn't handle. Concrete roads required expansion joints to accommodate thermal expansion and contraction. Without joints, concrete slabs would crack randomly as temperature changes caused dimensional changes. Engineers developed techniques for cutting control joints at regular intervals, typically every 15 to 20 feet, creating intentional weak points where cracks would form in straight lines rather than randomly. These joints were filled with compressible materials that allowed movement while preventing water infiltration. The choice between asphalt and concrete surfaces often reflected economic calculations and local conditions. Asphalt construction was generally less expensive initially and could be completed more quickly. Repairs were simpler, involving milling damaged sections and replacing them with fresh material. Concrete offered longer service life and required less maintenance but cost more to install and was difficult to repair. Cold climates favoured asphalt because freeze-thaw cycles could damage concrete, while hot climates sometimes favoured concrete because extreme heat could soften asphalt. By the 1920s, road construction had become a sophisticated engineering discipline employing mechanical equipment, standardized materials, and scientific design principles. The transition from hand-laid stone to machine-spread asphalt and concrete represented not just technical evolution, but a fundamental change in the scale and speed of road building, enabling the transportation networks that would define the 20th century. The mid-20th century witnessed the construction of highway systems on a scale unprecedented in human history. These networks transformed national economies, reshaped settlement patterns, and established engineering standards that would influence road construction globally. The projects represented not just infrastructure development, but fundamental reimagining of how transportation systems should function in modern industrial societies. Germany's Autobahn system, though conceived in the 1920s, saw extensive construction beginning in 1933. The design philosophy emphasized high-speed travel over long distances with minimal interruption. Access was limited to designated entrance and exit ramps rather than allowing connections at arbitrary points. Opposing traffic directions were separated by median strips, eliminating the risk of head-on collisions. Curves were designed with large radii to accommodate high speeds safely, and grades were kept gentle to prevent trucks from slowing traffic on hills. By 1942, approximately 2,400 miles of Autobahn had been completed. The Autobahn construction methods reflected German engineering precision. Roadbeds were excavated to depths of several feet, with soil conditions carefully analysed to determine foundation requirements. In areas with weak soils, engineers improved load-bearing capacity through soil stabilisation techniques, mixing lime or cement with native soil to increase strength. The pavement structure typically consisted of a foundation layer of large stones, a binding layer of smaller stones mixed with bitumen, and a surface layer of fine asphalt concrete. Total pavement thickness often exceeded 20 inches to support heavy truck traffic and prevent rutting. Italy developed its autostrada system during the same period, beginning with the Milano-Varese route opened in 1924. Italian engineers adapted highway design to mountainous terrain, creating tunnels and viaducts where German engineers might have routed roads around obstacles. The engineering challenges were substantial, requiring innovations in tunnel boring, bridge construction, and slope stabilisation. These projects demonstrated that limited access highways could be built even in topographically difficult regions, though at considerably higher cost. The United States Interstate Highway System, authorized by the Federal Aid Highway Act of 1956, became the largest public works project in history. President Dwight Eisenhower, influenced by his experience with the Autobahn during World War II, championed the system as essential for national defense and economic efficiency. The initial plan called for 41,000 miles of divided, limited-access highways connecting all cities with populations exceeding 50,000. The federal government would fund 90% of construction costs, with states covering the remainder. Interstate construction standards were precisely specified. Lanes were required to be 12 feet wide. Shoulders had to provide adequate space for disabled vehicles. Curves were designed for speeds of 50 to 70 miles per hour, depending on terrain. Grades couldn't exceed specified maximums, typically 3 to 5%. Vertical clearances at overpasses were set at 14 feet minimum to accommodate trucks. These standards ensured consistency across the entire system, allowing drivers to travel from Maine to California on roads built to identical specifications. The pavement design for interstate highways reflected accumulated knowledge about load distribution and material behavior. Engineers used flexible pavement design methods developed by the American Association of State Highway Officials, which calculated required pavement thickness based on expected traffic volume, axle loads, and subgrade strength. The typical interstate pavement consisted of a prepared subgrade, a base layer of crushed stone or gravel, and an asphalt concrete surface course. Total thickness varied by location, but commonly reached 12 to 18 inches. Soil mechanics had become sophisticated enough to predict how different soil types would perform under sustained loading. Engineers conducted laboratory tests on soil samples, determining properties such as California bearing ratio, which measured soil strength by testing resistance to penetration. Weak soils required either removal and replacement with engineered fill, or improvement through compaction and stabilization. This scientific approach to foundation design prevented many of the settlement and failure problems that had plagued earlier roads. Asphalt concrete technology advanced significantly during this period. Mixed design became a precise science, with engineers specifying exact proportions of aggregate, asphalt binder, and sometimes additives to achieve desired properties. The HVIM method and later the Marshall method provided standardized testing procedures to evaluate mixed designs before construction. Aggregates were graded by size distribution, with specifications requiring certain percentages of various size fractions to achieve optimal density and stability. The asphalt binder itself varied by climate. In cold regions, softer grades that remained flexible at low temperatures prevented thermal cracking. In hot climates, harder grades resisted rutting from heavy traffic on hot summer days. Engineers selected binder grades based on expected temperature ranges, using classification systems that indicated viscosity at standard test temperatures. This matching of materials to environmental conditions significantly improved pavement performance. Construction quality control became increasingly rigorous. Nuclear density gauges, introduced in the 1950s, allowed rapid measurement of compaction, ensuring that each layer met specified density requirements before the next layer was placed. Temperature monitoring ensured asphalt was placed within acceptable ranges for proper compaction. Core samples verified that finished pavement met thickness and density specifications. This level of quality assurance was impossible in earlier eras, but became standard practice for major highway projects. Concrete highway construction followed similar quality control principles. Mixed designs specified cement content, water-cement ratio, aggregate proportions, and sometimes admixtures to modify setting time or improve durability. Slump tests measured concrete workability before placement. Cylinder samples were cast during construction and tested for compressive strength to verify that concrete met design specifications. Reinforcing steel was positioned according to structural calculations, ensuring adequate cover to prevent corrosion while placing steel where tensile stresses would be highest. Bridge construction technology evolved to support highway systems. Pre-stressed concrete developed by Eugene Freycinet in France during the 1920s, but widely adopted after World War II, allowed longer spans with less material than conventional reinforced concrete. Steel tendons were tensioned before concrete was poured, creating internal compression that counteracted tensile stresses from traffic loads. This technique enabled graceful bridge designs with slender profiles, reducing visual impact while improving structural efficiency. Japan's expressway system, begun in 1957 with the Meishin Expressway connecting Nagoya and Kobe, demonstrated that modern highway networks could be built in densely populated nations with limited land area. Japanese engineers developed efficient interchanges requiring minimal land acquisition and pioneered elevated urban expressways that utilized airspace above existing streets. Construction in seismically active regions required special attention to earthquake resistance, with flexible pavement designs and bridge structures engineered to withstand ground motion without catastrophic failure. By the 1970s, industrialized nations had largely completed their primary highway networks. The engineering knowledge accumulated during this construction boom established principles that would guide road building for decades. Understanding of materials behavior, structural design, quality control, and construction methods had reached levels of sophistication that would have seemed impossible a century earlier. The challenge would shift from building new networks to maintaining and upgrading existing infrastructure as traffic volumes continued to grow. The enthusiasm that accompanied highway construction in the mid-20th century gradually gave way to a sobering recognition that maintaining these vast networks presented challenges as complex as building them. Roads deteriorate through multiple mechanisms, each requiring different interventions. Understanding these deterioration processes became essential as infrastructure aged and maintenance budgets struggled to keep pace with needs. Asphalt pavements age through oxidation, a chemical process in which atmospheric oxygen reacts with the asphalt binder, making it progressively more brittle. Fresh asphalt contains oils and resins that provide flexibility, allowing pavement to bend slightly under loads without cracking. Over years of exposure to sunlight and air, these volatile components evaporate or chemically transform, leaving behind a harder, less flexible material. Oxidized asphalt develops surface cracks, initially small but widening and deepening over time. Water penetrates these cracks, accelerating deterioration by weakening underlying layers and causing additional damage through freeze-thaw cycles in cold climates. Rutting, the formation of depressions in wheel paths, results from repeated loading by heavy vehicles. Each time a truck passes, the pavement compresses slightly. In hot weather, asphalt softens, and if the pavement lacks adequate strength, permanent deformation accumulates. Ruts collect water, creating hydroplaning hazards and accelerating pavement breakdown. Deep ruts require extensive repair, often involving removal and replacement of the affected pavement layers. Fatigue cracking develops from the bottom of asphalt layers upward, caused by repeated bending under traffic loads. Each vehicle passage creates stress cycles, and though individual stresses may be small, accumulated cycles eventually exceed the pavement's fatigue resistance. These cracks appear on the surface as interconnected patterns resembling alligator skin, indicating that the pavement structure has reached the end of its functional life. Repair typically requires full reconstruction rather than surface treatments. Concrete pavements deteriorate through different mechanisms. Joints and cracks allow water to infiltrate, and if drainage is inadequate, water accumulates beneath the slab. When heavy vehicles pass over sections with voids underneath, the concrete flexes more than designed, creating pumping action that forces water and fine soil particles out through joints and cracks. This pumping gradually enlarges voids, leading to loss of support. Eventually, the unsupported concrete breaks under traffic loads, creating potholes or requiring slab replacement. Concrete also suffers from scaling, where the surface deteriorates due to freeze-thaw damage, particularly in regions where de-icing salts are applied. Salt lowers the freezing point of water, but it also creates osmotic pressure that draws water into the concrete's pore structure. When this water freezes, expansion forces exceed the concrete's tensile strength, causing surface layers to flake away. Air entrainment, the intentional incorporation of microscopic air bubbles in concrete mix designs, provides space for ice to expand without damaging the concrete matrix. But older pavements often lack this protection. The economic reality of road maintenance became apparent in the 1970s and 80s as the interstate highway system matured. Traffic volumes exceeded original projections, particularly for heavy trucks. Many states had deferred maintenance during initial construction phases, expecting to address needs after networks were complete. The combination of aging pavements, heavy use, and limited budgets created a maintenance crisis that persisted for decades. Engineers developed pavement management systems to allocate limited maintenance funds optimally. These systems rated pavement condition through surveys measuring roughness, cracking, rutting, and other distress indicators. The data allowed engineers to predict deterioration rates and prioritize projects based on cost effectiveness. A pavement in fair condition might be maintained with relatively inexpensive surface treatments, while waiting until it reached poor condition could require costly reconstruction. This worst first versus preventive maintenance debate shaped infrastructure policy. Preventive maintenance techniques aim to extend pavement life at relatively low cost. Crack sealing prevented water infiltration by filling cracks with hot rubberized asphalt or other sealants. Fog seals, thin applications of diluted asphalt emulsion, replaced oils lost to oxidation and sealed the surface against water. Chip seals, single layers of asphalt with aggregate pressed into the surface, provided skid resistance and waterproofing. These treatments cost a fraction of reconstruction, but required timely application before deterioration progressed too far. More substantial rehabilitation techniques addressed pavements with significant distress. Milling removed the surface layer of asphalt pavement, creating a uniform profile for new overlay while leaving the structural foundation intact. The milled material, called reclaimed asphalt pavement, could be recycled into new asphalt mixes, reducing material costs and environmental impact. Overlays added new asphalt layers to restore smoothness and structural capacity, though increasing pavement thickness created challenges at bridges and intersections where vertical clearances had to be maintained. Full-depth reclamation, developed in the 1980s, offered an alternative to complete reconstruction. Specialized equipment pulverized existing asphalt and base layers to a depth of 12 inches or more, mixing them together. Cement or asphalt emulsion was added to stabilize the blended material, which was then compacted and surfaced. This technique salvaged existing materials while creating a strong foundation, reducing both cost and environmental impact compared to removing old pavement to landfills and importing new materials. Concrete pavement rehabilitation presented different challenges. Diamond grinding restored surface smoothness by cutting away a thin layer with closely spaced diamond saw blades, removing bumps and providing excellent skid resistance. This technique extended concrete pavement life significantly at moderate cost. More severely damaged concrete sometimes received asphalt overlays, though differential movement between concrete slabs and asphalt could cause reflection cracking unless special interlayers were used to absorb movement. The development of perpetual pavement concepts in the 1990s sought to minimize future maintenance costs. These designs employed thick, strong base layers designed to last indefinitely, with thinner surface courses that could be milled and replaced periodically. The theory held that if the foundational structure never fatigued, maintenance would consist of surface renewal rather than structural rehabilitation. Several jurisdictions built experimental perpetual pavement sections and monitored their performance to validate design assumptions. Seasonal maintenance requirements consumed substantial resources, particularly in northern climates. Winter maintenance involved snow ploughing, de-icing, and repairing damage from freeze-thaw cycles and snowplow operations. De-icing chemicals, while improving safety, accelerated concrete deterioration and contaminated groundwater. Alternative de-icing materials, such as calcium magnesium acetate or beet juice derivatives, were tested, offering environmental benefits but at higher cost. Some agencies experimented with heated pavement systems, embedding electrical resistance wires or hydronic tubing to melt snow, though energy costs limited widespread adoption. Bridge maintenance represented a specialized subset of road infrastructure challenges. The collapse of the Silver Bridge connecting Ohio and West Virginia in 1967, killing 46 people, prompted the National Bridge Inspection Program requiring regular structural assessments. Inspectors evaluated condition ratings for deck, superstructure, and substructure components, identifying deterioration before it compromised safety. Bridge preservation techniques included deck overlays, bearing replacement, structural steel repainting, concrete repair, and seismic retrofitting in earthquake-prone regions. The realization that maintenance had been systematically underfunded led to calls for increased investment in the late 20th century. Studies documented that deferring maintenance resulted in exponentially higher future costs, with reconstruction costing 5 to 10 times more than timely preservation treatments. Despite this economic logic, political pressures often favored visible new construction over less glamorous maintenance activities. The challenge of funding adequate maintenance while accommodating traffic growth on aging infrastructure would define road management for coming decades. The late 20th and early 21st centuries saw the development of specialized roads designed for purposes far removed from ordinary transportation. These engineering achievements pushed the boundaries of what pavement could support, demonstrating how fundamental principles could be adapted to extraordinary demands. The NASA crawlaway at Kennedy Space Center in Florida represents perhaps the most remarkable specialized road ever constructed. Built in the mid-1960s to transport the Saturn V rocket and mobile launcher platform to launch pads, this road had to support loads that exceeded anything previously attempted. The combined weight of the crawler transporter, mobile launcher platform, and fully fueled Saturn V rocket approached 18 million pounds, distributed across 8 tank-like treads. The crawlaway consists of 2 parallel lanes, each 40 feet wide, stretching 3.5 miles from the Vehicle Assembly Building to Launch Complex 39. The road's foundation extends to bedrock, requiring excavation through layers of sand and shell to reach limestone at depths varying from 20 to 45 feet. Workers removed unstable material and backfilled with hydraulically placed sand, compacting it in lifts to create a stable base. Above this foundation sits several feet of crushed stone, graded and compacted to precise specifications. The surface layer of the crawlaway uses river rock rather than conventional aggregate. These stones, imported from Alabama, were selected for their exceptional hardness and durability. The rocks, 8 inches in diameter, are laid by hand in a matrix of asphalt cement, creating a surface capable of distributing the enormous point loads from the crawler treads. The total depth of the road structure reaches 7 feet, with every component engineered to prevent settlement or failure under sustained loading. The surface must remain level within extremely tight tolerances because any unevenness could cause the towering rocket to sway dangerously during transport. Maintenance of the crawlaway requires constant attention. After each use, crews inspect the surface for displacement or damage, replacing individual stones as needed. The top layer is periodically stripped and rebuilt to maintain structural integrity. Between major missions, the road essentially requires reconstruction, a testament to the extreme stresses imposed even by a structure designed for these loads. The crawler moves at a maximum speed of 1 mile per hour when loaded, taking approximately 6 hours to complete the journey to the launch pad. Airport runway construction represents another category of specialized pavement design. Modern runways must support aircraft weighing up to 1 million pounds or more, with loads concentrated on landing gear configurations that create intense stresses. The Airbus A380, introduced in 2005, has a maximum takeoff weight of 1,268,000 pounds distributed across 22 wheels. Runway pavements must absorb impact loads from landing, resist abrasion from tyres, and maintain smoothness to prevent dangerous oscillations during takeoff and landing. Runway pavement design uses sophisticated computer modelling to predict stress distribution under various aircraft types and loading conditions. The Federal Aviation Administration specifies design procedures that account for the number and weight of operations over the pavement's design life, typically 20 years. Runway pavements are often 2 to 3 feet thick, with multiple layers of materials selected for their load-bearing properties. Portland cement concrete is preferred for heavy aircraft because of its stiffness and load-distributing capability, though asphalt runways exist at smaller airports with lighter traffic. The concrete mix designs for runways incorporate specifications for extremely high strength, often exceeding 5,000 pounds per square inch compressive strength. High early strength formulations allow repairs to be completed during overnight closures, minimizing disruption to airport operations. Surface texture is carefully controlled to provide adequate friction for braking aircraft while minimizing tire wear and noise. Grooving, shallow channels cut perpendicular to the runway direction, helps drain water and prevents hydroplaning during wet conditions. Mining operations in remote locations required development of heavy haul roads capable of supporting trucks carrying hundreds of tons of ore. The Pilbara region of Western Australia, where iron ore mines operate in an extremely harsh climate with temperatures exceeding 45 degrees Celsius, presented particular challenges. Mining companies constructed private road networks spanning hundreds of miles, designed for trucks with payloads exceeding 300 tons. These mining roads employ pavement structures up to 6 feet thick, with special attention to subgrade preparation and drainage. The intense heat requires asphalt binders, modified with polymers, to prevent rutting and bleeding. Some operations use concrete pavements despite higher initial costs because maintenance windows are limited, and concrete offers superior performance under sustained heavy loading. Road maintenance is scheduled meticulously because equipment downtime costs mining operations millions of dollars per day. Developments in construction technology transformed road building efficiency and quality. Automated machine guidance systems, introduced in the early 2000s, use GPS and laser sensors to control grading equipment with centimetre-level precision. Operators no longer rely solely on stakes and string lines, but receive real-time feedback on blade position relative to design grade. This automation improved accuracy while reducing construction time and labour requirements. Intelligent compaction systems, developed in Europe in the late 1990s and adopted increasingly worldwide, measure pavement density in real time during rolling operations. Vibratory rollers equipped with accelerometers detect how soil or asphalt responds to compaction effort, identifying weak spots that require additional rolling. The system produces continuous maps showing compaction levels across the entire project, replacing random spot checks with comprehensive documentation. This technology significantly improved quality control while reducing the risk of inadequately compacted areas that would fail prematurely. Warm mix asphalt technologies, commercialized in the early 2000s, reduced mixing and laying temperatures by 30 to 75 degrees Fahrenheit compared to traditional hot mix asphalt. Chemical additives or foaming processes reduced asphalt viscosity at lower temperatures, allowing proper coating of aggregates and adequate workability during placement. The lower temperatures reduced fuel consumption, emissions, and worker exposure to fumes while extending the paving season in cold climates and allowing longer haul distances from plant to project. Recycling technologies advanced substantially, with reclaimed asphalt pavement and recycled concrete aggregate increasingly used in new construction. Cold-in-place recycling trains milled existing asphalt pavements, mixed the reclaimed material with emulsified asphalt or other stabilizing agents, and relayed it in a single operation. This technique rehabilitated deteriorated roads while minimizing material transportation and reducing environmental impact. Some agencies achieved recycling rates exceeding 90%, essentially rebuilding roads from their own materials. Geosynthetic materials expanded the possibilities for road construction in challenging conditions. Geogrids, polymer meshes with high tensile strength, reinforced base layers and distributed loads more effectively, allowing reduced pavement thickness or construction over weak soils. Geotextiles separated dissimilar soil layers, preventing intermixing while allowing water drainage. These materials enabled road construction in locations previously considered unsuitable, such as wetlands or soft clay deposits. Permeable pavements, designed to allow water infiltration rather than runoff, address concerns about stormwater management and groundwater recharge. These systems used open-graded asphalt or concrete with interconnected voids, or permeable pavers with gaps between units, allowing water to percolate into underlying stone reservoirs. While not suitable for high-traffic highways, permeable pavements found applications in parking lots, low-volume roads, and urban areas where stormwater management was critical. The convergence of materials science, sensor technology, automation, and environmental awareness transformed road construction from a process of spreading and compacting materials to a sophisticated engineering discipline employing advanced monitoring and control systems. Roads built in the early 21st century incorporated technologies and materials that would have seemed impossible decades earlier, yet the fundamental principles of load distribution, drainage, and compaction remained as relevant as they had been in Roman times. The late 20th and early 21st centuries saw the development of specialized roads designed for purposes far removed from ordinary transportation. These engineering achievements pushed the boundaries of what pavement could support, demonstrating how fundamental principles could be adapted to extraordinary demands. The NASA crawlaway at Kennedy Space Center in Florida represents perhaps the most remarkable specialized road ever constructed. Built in the mid-1960s to transport the Saturn V rocket and mobile launcher platform to launch pads, this road had to support loads that exceeded anything previously attempted. The combined weight of the crawler transporter, mobile launcher platform, and fully fueled Saturn V rocket approached 18 million pounds, distributed across 8 tank-like treads. The crawlaway consists of 2 parallel lanes, each 40 feet wide, stretching 3.5 miles from the Vehicle Assembly Building to Launch Complex 39. The road's foundation extends to bedrock, requiring excavation through layers of sand and shell to reach limestone at depths varying from 20 to 45 feet. Workers removed unstable material and backfilled with hydraulically placed sand, compacting it in lifts to create a stable base. Above this foundation sits several feet of crushed stone, graded and compacted to precise specifications. The surface layer of the crawlaway uses river rock rather than conventional aggregate. These stones, imported from Alabama, were selected for their exceptional hardness and durability. The rocks, 8 inches in diameter, are laid by hand in a matrix of asphalt cement, creating a surface capable of distributing the enormous point loads from the crawler treads. The total depth of the road structure reaches 7 feet, with every component engineered to prevent settlement or failure under sustained loading. The surface must remain level within extremely tight tolerances because any unevenness could cause the towering rocket to sway dangerously during transport. Maintenance of the crawlaway requires constant attention. After each use, crews inspect the surface for displacement or damage, replacing individual stones as needed. The top layer is periodically stripped and rebuilt to maintain structural integrity. Between major missions, the road essentially requires reconstruction, a testament to the extreme stresses imposed even by a structure designed for these loads. The crawler moves at a maximum speed of 1 mile per hour when loaded, taking approximately 6 hours to complete the journey to the launch pad. Airport runway construction represents another category of specialized pavement design. Modern runways must support aircraft weighing up to 1 million pounds or more, with loads concentrated on landing gear configurations that create intense stresses. The Airbus A380, introduced in 2005, has a maximum takeoff weight of 1,268,000 pounds distributed across 22 wheels. Runway pavements must absorb impact loads from landing, resist abrasion from tyres, and maintain smoothness to prevent dangerous oscillations during takeoff and landing. Runway pavement design uses sophisticated computer modelling to predict stress distribution under various aircraft types and loading conditions. The Federal Aviation Administration specifies design procedures that account for the number and weight of operations over the pavement's design life, typically 20 years. Runway pavements are often 2 to 3 feet thick, with multiple layers of materials selected for their load-bearing properties. Portland cement concrete is preferred for heavy aircraft because of its stiffness and load-distributing capability, though asphalt runways exist at smaller airports with lighter traffic. The concrete mix designs for runways incorporate specifications for extremely high strength, often exceeding 5,000 pounds per square inch compressive strength. High early strength formulations allow repairs to be completed during overnight closures, minimizing disruption to airport operations. Surface texture is carefully controlled to provide adequate friction for braking aircraft while minimizing tire wear and noise. Grooving, shallow channels cut perpendicular to the runway direction, helps drain water and prevents hydroplaning during wet conditions. Mining operations in remote locations require development of heavy haul roads capable of supporting trucks carrying hundreds of tons of ore. The Pilbara region of Western Australia, where iron ore mines operate in an extremely harsh climate with temperatures exceeding 45 degrees Celsius, presented particular challenges. Mining companies constructed private road networks spanning hundreds of miles, designed for trucks with payloads exceeding 300 tons. These mining roads employ pavement structures up to 6 feet thick, with special attention to subgrade preparation and drainage. The intense heat requires asphalt binders modified with polymers to prevent rutting and bleeding. Some operations use concrete pavements despite higher initial costs because maintenance windows are limited, and concrete offers superior performance under sustained heavy loading. Road maintenance is scheduled meticulously because equipment downtime costs mining operations millions of dollars per day. Developments in construction technology transformed road building efficiency and quality. Automated machine guidance systems, introduced in the early 2000s, use GPS and laser sensors to control grading equipment with centimetre-level precision. Operators no longer rely solely on stakes and string lines, but receive real-time feedback on blade position relative to design grade. This automation improved accuracy while reducing construction time and labour requirements. Intelligent compaction systems, developed in Europe in the late 1990s and adopted increasingly worldwide, measure pavement density in real time during rolling operations. Vibratory rollers equipped with accelerometers detect how soil or asphalt responds to compaction effort, identifying weak spots that require additional rolling. The system produces continuous maps showing compaction levels across the entire project, replacing random spot checks with comprehensive documentation. This technology significantly improved quality control while reducing the risk of inadequately compacted areas that would fail prematurely. Warm mix asphalt technologies, commercialized in the early 2000s, reduced mixing and laying temperatures by 30 to 75 degrees Fahrenheit compared to traditional hot mix asphalt. Chemical additives or foaming processes reduced asphalt viscosity at lower temperatures, allowing proper coating of aggregates and adequate workability during placement. The lower temperatures reduced fuel consumption, emissions, and worker exposure to fumes while extending the paving season in cold climates and allowing longer haul distances from plant to project. Recycling technologies advanced substantially, with reclaimed asphalt pavement and recycled concrete aggregate increasingly used in new construction. Cold in-place recycling trains milled existing asphalt pavements, mixed the reclaimed material with emulsified asphalt or other stabilizing agents, and relayed it in a single operation. This technique rehabilitated deteriorated roads while minimizing material transportation and reducing environmental impact. Some agencies achieved recycling rates exceeding 90%, essentially rebuilding roads from their own materials. Geosynthetic materials expanded the possibilities for road construction in challenging conditions. Geogrids, polymer meshes with high tensile strength, reinforced base layers and distributed loads more effectively, allowing reduced pavement thickness or construction over weak soils. Geotextiles separated dissimilar soil layers, preventing intermixing while allowing water drainage. These materials enabled road construction in locations previously considered unsuitable, such as wetlands or soft clay deposits. Permeable pavements, designed to allow water infiltration rather than runoff, addressed concerns about stormwater management and groundwater recharge. These systems used open-graded asphalt or concrete with interconnected voids, or permeable pavers with gaps between units, allowing water to percolate into underlying stone reservoirs. While not suitable for high-traffic highways, permeable pavements found applications in parking lots, low-volume roads, and urban areas where stormwater management was critical. The convergence of material science, sensor technology, automation, and environmental awareness transformed road construction from a process of spreading and compacting materials to a sophisticated engineering discipline employing advanced monitoring and control systems. Roads built in the early 21st century incorporated technologies and materials that would have seemed impossible decades earlier, yet the fundamental principles of load distribution, drainage, and compaction remained as relevant as they had been in Roman times. The future of roads extends beyond incremental improvements to existing technologies, encompassing fundamental reconceptualization of what roads are and how they function. Emerging concepts suggest that roads will become active participants in transportation systems rather than passive infrastructure, adapting dynamically to changing conditions and integrating seamlessly with vehicles and broader urban systems. Autonomous vehicles will reshape road design requirements profoundly. Self-driving cars rely on precise lane markings, consistent signage, and predictable road geometry for navigation. Current roads, designed for human drivers who can interpret ambiguous situations and compensate for poor markings, may prove inadequate for sensors and algorithms. Future roads might incorporate high-contrast markings visible to cameras and LiDAR systems under all weather conditions, embedded markers that communicate position through radio frequency identification, and standardized geometry that simplifies navigation algorithms. The transition to autonomous vehicles could enable narrower lanes because computer-controlled cars maintain position more precisely than human drivers. Traffic capacity might increase on existing roads without widening if autonomous vehicles travel closer together at coordinated speeds. Intersections might operate without traffic signals, with vehicles communicating wirelessly to coordinate passage through crossing points at full speed. These efficiency gains could reduce the need for new road construction while improving traffic flow on existing infrastructure. Adaptive roads that reconfigure based on traffic demand represent another frontier. Reversible lanes, where direction changes based on traffic patterns, already exist on some highways, but future systems might dynamically adjust lane width, create temporary bus lanes during peak periods, or designate lanes for specific vehicle types. Digital signage and automated barriers could implement changes rapidly in response to real-time conditions. Roads might even incorporate modular surfaces that could be repositioned to alter geometry as needs evolve. Climate change adaptation will dominate road engineering in coming decades. Rising temperatures, more intense precipitation events, and changing freeze-thaw cycles will stress infrastructure designed for historical climate conditions. Pavements in regions experiencing increased heat will require harder asphalt grades to prevent rutting, while areas with intensifying storms will need enhanced drainage capacity. Coastal roads face threats from sea level rise and more frequent storm surge, requiring elevation, hardening, or eventual abandonment. Engineers are developing climate-resilient design standards, incorporating projected future conditions rather than historical data. Precipitation intensity for 50-year storms used to size drainage systems may increase substantially in many regions. Temperature ranges for selecting asphalt binder grades are expanding. Some jurisdictions are testing pavements designed for climate conditions expected decades in the future, accepting that they may be suboptimal for current conditions but will perform better as climate changes. Carbon sequestration in road materials offers potential for infrastructure to mitigate rather than merely adapt to climate change. Concrete can absorb carbon dioxide from the atmosphere through carbonation, though the process is slow and only partially offsets emissions from cement production. Researchers are exploring concrete formulations that maximize carbon uptake and investigating injection of captured carbon dioxide into concrete during curing to accelerate sequestration. While unlikely to make roads carbon negative, given construction and maintenance emissions, these approaches could significantly reduce net carbon footprint. Self-healing concrete incorporating bacteria represents an innovative durability strategy. Dormant bacteria embedded in concrete during mixing activate when cracks allow water penetration, consuming nutrients also incorporated in the mix and producing limestone that fills cracks autonomously. This biological healing could extend concrete service life significantly, reducing maintenance costs and resource consumption. Field trials in Europe and Asia are monitoring performance over time to validate long-term effectiveness and durability of the healing mechanism. Graphene-enhanced asphalt demonstrates how nanomaterials might improve pavement properties. Graphene, single-atom thick sheets of carbon with exceptional strength and conductivity, can be mixed into asphalt in tiny quantities to improve mechanical properties, thermal conductivity, and electrical conductivity. Stronger asphalt allows thinner pavements or longer service life. Enhanced thermal conductivity could improve de-icing performance or allow roads to serve as heat exchangers for buildings. Electrical conductivity might enable roads to sense their own condition through resistance changes or support vehicle charging. Laboratory results show promise, though production costs currently limit practical application. Modular road construction systems envision factory-built pavement sections transported to sites and assembled like building blocks. Precast concrete panels or prefabricated asphalt modules could be manufactured under controlled conditions, ensuring quality and incorporating sensors, heating elements, or other features difficult to install conventionally. Modular construction would dramatically reduce installation time, minimizing traffic disruption in urban areas. Damaged sections could be replaced quickly without extensive reconstruction. The Netherlands has experimented with prefabricated concrete pavement systems, demonstrating technical feasibility, though cost competitiveness with conventional construction remains uncertain. Hyperloop and other high-speed ground transportation systems under development will require entirely new categories of infrastructure. These systems, envisioning passenger capsules travelling through low-pressure tubes at speeds exceeding 700 miles per hour, demand extraordinarily smooth, stable guideways, maintaining precise alignment across long distances. The engineering challenges resemble railway construction more than traditional roads, but represent evolution of ground transportation infrastructure toward higher speeds and efficiencies impossible on conventional roads. Urban air mobility, using electric vertical takeoff and landing aircraft for passenger transport, could reduce dependence on roads in dense cities. While not roads in the traditional sense, vertiports for these vehicles require infrastructure for landing, charging, and passenger boarding. The interaction between aerial and ground transportation systems will require coordination, potentially reducing road traffic while creating new infrastructure categories. The concept of roads as data infrastructure gained traction as connected and autonomous vehicles proliferated. Roads equipped with comprehensive sensor networks could monitor traffic flow, structural condition, weather, and countless other parameters, transmitting data to cloud-based systems that optimize traffic management, predict maintenance needs, and enhance safety. This digital layer transforms roads from physical infrastructure into cyber-physical systems where information flow is as important as vehicle movement. Circular economy principles applied to road construction emphasize designing materials and systems for eventual recovery and reuse rather than disposal. Future roads might be constructed entirely from materials engineered for multiple life cycles, with components easily separated and reclaimed. Asphalt and concrete would be designed for high recyclability, with additives that facilitate separation and cleaning. This approach requires thinking beyond the initial construction to consider eventual deconstruction and material flows over multiple generations of infrastructure. The question of whether roads themselves will remain necessary in their current form remains open. Autonomous vehicle technology might enable transportation systems that operate more like elevators, with vehicles summoned on demand rather than individually owned, potentially reducing the number of vehicles and required road capacity. Virtual reality technology could reduce travel demand for meetings and social interactions. Localized production through advanced manufacturing might decrease freight transportation needs. These changes could alter the role of roads in society fundamentally. Yet the probability remains high that physical movement of people and goods will continue requiring robust infrastructure. The principles that guided ancient road builders, understanding of load distribution, water management, and material properties will endure even as specific technologies evolve. Roads have enabled human civilization to expand, economies to develop, and societies to connect across distances. Their future incarnations, incorporating sensors, sustainability, adaptability, and intelligence, will continue serving these essential functions while addressing challenges their builders could never have imagined. The path from animal trails to smart highways demonstrates humanity's persistent drive to ease movement across the Earth's surface, a drive unlikely to diminish as long as people have places they need to go.